Hi there, my name is Charles Subasfani Msipa. Welcome to another presentation of complex integration. That is the application of what is called the Cauchy integral formula or Cauchy integral theorem, which is summarized here as follows. The first version which we have got here, just recapping what we've seen before. The statement of the theorem says that if you've got this kind of a situation, which is a rational expression here, with a kind of an isolated pole like that, whereby the numerator fz is analytic in and on the closed simple curve C, the integral is evaluated as 2 pi I multiplied by f at z0. Note that this as z0 here is this pole there. And in the case f of z is n times differentiable, the integral is evaluated this way. It is equal to 2 pi I multiplied by the nth derivative of f of z evaluated at the pole there. As you can see, the pole here is a repeated pole, repeated n plus 1 times, and the function is required to be differentiable n times. So I wanted to discuss with you examples which involve the two theorems, and at the same time I would like to exploit the examples which I'm going to use to land at what we're going to call the residue theorem. Okay, let's start from following. Let's say we've got an integral. So we've got here an integral of z over z plus 3 multiplied by z minus 2. And then clearly we've got the poles here are minus 3 and minus 2. So let's first of all assume that this curve contains both poles minus 3 and 2. So what we're going to do, we're going to integrate via this formula. So what we're going to say, let's say this integral is equals to the integral over a simple closed curve gamma 1, which encloses, let's say, one pole. In this case, let's choose z 0 equals to minus 3. So we have here z in the numerator, z minus 2 dz plus, I'm trying to be quick here because we've seen this before. So what we've done here, we say this integral is going to be equal to the sum of integrals around the simple closed curve, each closed curve enclosing only a single pole. In this case, this pole will be that. And you must notice that this expression which is here is exactly equal to that, reminding you that we said before, if you've got B over AC, this is equals to B over A over C, and also equals to B over C over A. That's what we're using there. So writing this, next part, you say this will be integral over gamma 2. In this case, we're going to isolate one pole, which is going to be 2. So write here z minus 2 dz, and you are going to have z over z plus 3. So what the manipulation we have done here is to make the this expression obvious so that you can apply that theorem. So in this case, what is going to happen here is going to be this, taking note of the fact that this closed curve contains only single pole minus 3, then this expression here, which plays the role of fz there, should be analytic in and on this curve. So applying the formula here, we're going to have 2 pi I multiplied by f of z. I'm going to copy this exactly as it is, z minus 2, evaluated, that straight line, they say evaluated at z equals to minus 3, plus, this side is going to be same formula, 2 pi I multiplied by fz. In this case, our fz is z over z plus 3, z over z plus 3, evaluated at z equals to 2. Now, evaluating this integral, we can see that we've got a common factor here, 2 pi I. So I'm going to choose to write this 2 pi I here as a common factor. And then inside here, I'm going to evaluate this minus 3 over minus 3 minus 2 plus, here's going to be 2 over 2 plus 3, and then what we're going to have here is this is going to be 3 over 5, because this is negative over negative, 3 over 5, and they're going to have 2 over 5. Then let's say this is 2 pi I, 3 over 5 plus 2 over 5, which you can clearly see that this gives us 1. Then this is 2 pi I multiplied by 1, which is equals to 2 pi I. Now, at this point, I would like to leave this as it is and try to do some kind of experiment here. What the experiment I want to do here is to look at the function f of z equals to z over z plus 3 multiplied by z minus 2. And you'll notice that the poles are minus 3 and 2. So knowing from what you did before, we know that at poles we can calculate the residues of the rational expression. So let's start by calculating the residue of this f of z at minus 3. Then we write this way, say residue. This is just notation. Residue of f of z at z equals to minus 3. And this is a simple pole. This is equal to the limit as z is going to minus 3 of z minus minus 3, which is plus 3 multiplied by f of z. Then this gives us limit as z is going to minus 3 of z over z minus 2. And we see that if we evaluate this limit by plugging in, we don't get any undefined situation, so we can continue to evaluate. What we get here, we get minus 3 over minus 3 minus 2, which gives us 3 over 5. So this is a residue. Then next we'll follow the residue of f of z at z equals 2, at z equals to 2, in which case we're going to multiply this expression by z minus 2, which gives us z over z plus 3, and we calculate the limit of z over z plus 3 as z is going to 2, it's approaching 2, and we get here that this is 2 over 2 plus 3, which is 5. Now, what we've done here, we want to compare what we've got here with what the results we've got this side. So let me just draw kind of a div here. So what we're calculating here are actually residues of the function which is being integrated and the integral sign there. So what we observe, this integral evaluated according to Cauchy integral theorem took us through these parts. We evaluated there, we got 3 over 5. Incidentally, there also got 3 over 5 as a residue. And evaluating this part of integral, we got 2 over 5, and which is our residue there. Now, if you check the expression we've got here, comes from this situation here where we've got our fz being that, and also the result we got there come from this situation whereby our f of z is this part. So this little experiment we've done here leads us to a conclusion that integrating a function using Cauchy's integral formula in this case actually is the same as adding the residues, which you see there, and multiplied by 2 pi I. And this, guys, is actually, it's a fact, it's a theorem. I just sort of made you experience what happens in the theorem before actually announcing the theorem. The theorem actually states that an integral of a complex function with poles which are enclosed in a simple closed curve is actually going to be the sum of the residues. I said the sum. That is the sum of the residues multiplied by 2 pi I. So I would like you to refer to your textbook and see the real statement of this theorem, which we are going to call the residue theorem. So at this point, what I can say is we've got 2 approaches to integration. In this case, we can either use the Cauchy integral theorem as we have applied it there, or we can use this observation, which we now call the residue theorem for complex integration, which says an integral is going to be the sum of the residues multiplied by 2 pi I. For now, I would like to say thank you for listening. We meet again during the discussion of the next example. Otherwise, bye-bye.